mmWave is an essential 5G technology enabler and a complementary building block of a high-performance 5G system. Today, it is already delivering extreme capacity and multi-gigabit per second speeds for enhanced mobile broadband, but its role will expand as we pave the way to the future of 5G and beyond. In this video, we will focus on several key areas of mmWave evolution.
At Qualcomm Technologies, we are committed to making mmWave a commercial success. One common challenge that operators face is how to arrive at the most efficient network topology. Today, I will share with you two compelling illustrations of how mmWave networks can be planned and deployed intelligently, ensuring good coverage and exceptional mobile user experience. Our approach involves three steps. First, we create a digital twin of our targeted deployment based on readily available databases, such as Google Street View. Then, we simplify our digital model using machine learning-based object recognition, clustering, and pruning for computational efficiency. Last, we jointly evaluate placement location and the different mmWave infrastructure options to arrive at the most optimal topology. Here we see an outdoor coverage design for an approximately 1.5 square kilometer area of downtown Philadelphia. We can specify design constraints such as types of mmWave infrastructure available, from small cells and IAB to simple and smart repeaters, their cost ratios, and the level of coverage desired. Our approach then jointly determines optimum locations and the type of node to deploy at each selected location based on these constraints. Here, we see how an operator can evaluate cost and performance benefits of deploying simple and smart repeaters along with small cells. A well-planned network can greatly enhance user experience even in challenging settings. In this illustration, the user traverses through urban streets. Coverage and high data rates are ensured by various small cells and smart repeaters. Beam management algorithms and protocols in the network and device allow the user to seamlessly and dynamically connect to the best nodes and beams, thereby ensuring a consistently high level of performance. In conclusion, we are taking a comprehensive approach to designing and optimizing 5G mmWave networks. We combine machine learning and optimization techniques to greatly simplify the network planning process. Our scalable methodology extends to other deployment settings and joint designs with sub-7 GHz frequency bands to deliver compelling user experience at achievable costs.
We continue to drive foundational enhancements to 5G mmWave systems. This demonstration showcases mobility enhancements that can further improve performance, which is especially important for demanding use cases such as mobile VR, where any lag or service interruption can have significant impact to user experience. Here is the setup of our system simulation. We use an example deployment in Frankfurt, which operates in the 26 GHz band with 400 MHz of bandwidth. We have a mobile VR user that travels across the city on various predetermined routes. The network is loaded with other mmWave devices to emulate real-life network conditions. In the baseline scenario, the system utilizes L3 mobility management, in which the VR device experiences a longer handover latency when it moves from one cell to the next, resulting in lags and even interrupted services. With L1, L2 mobility management, inter-cell handovers can be better managed, thereby minimizing impacts to the application performance. We can see in the GUI that the user experience is superior with L1, L2 mobility, as confirmed by the user-perceived downlink data throughput, whereas L3 mobility experiences throughput dips during handovers. In conclusion, improvements in mobility play an important role in ensuring the quality of services of the applications. We will continue to drive new enhancements to mmWave systems, so stay tuned for more.
We've also been working on improving how spectrum can be shared between users for better spectrum utilization and quality of service. Licensed spectrum provides good quality of service, but it's often unutilized. Shared spectrum with dynamic access improves spectrum utilization, but it's reliant on connectivity to access control infrastructure and databases for the coordinated allocation of channels, which adds operational overhead and complexity. Finally, unlicensed spectrum with uncoordinated sharing offers deployment flexibility and the least operational complexity or overhead, but access to the channel is never guaranteed and quality of service degrades with network load. We demonstrate a new technology-neutral method for sharing the 37 to 37.6 GHz frequency band by allocating priority licenses for primary use instead of exclusive use. We also allow license holders to access other channels with secondary priority without degrading their service. We mitigate interference by using long-term sensing, or LTS, where devices transmit periodic signals for each operator to detect. When one or more operators use secondary channels and their beams overlap, they receive one of the periodic signals transmitted by the interfered devices. The operators then suspend the secondary channels and devices continue operating without interference and with high quality of service on their primary channels. Looking at the airport terminal simulation scenario with two operators, each with 6G Node Bs, 200 MHz bandwidth, and 32 antenna elements, we see spectrum sharing offers significantly higher network capacity than the unshared spectrum baseline, but LTS sharing offers much higher quality of service for a better user experience.